What's up? This is Dr. Mikey Park, coming to you from the University of Washington. Today I want to give you a brief introduction to particle physics and tell you some of the things that you're going to need to know in order to help us discover new particles of nature at the QuarkNet Masterclass next week. Let's start at the beginning. What exactly is a particle? Particles are the fundamental building blocks of everything in the universe. Everything is made up of particles. For example, consider a familiar object like a tree. If we were to zoom into the tree, into microscopic length scales, we would see that the tree is actually made up of billions and billions of particles called atoms. The most common atom inside of a tree is the hydrogen atom, and the hydrogen atom consists of two smaller particles, one called the electron, labeled here by the letter E, and another called the proton, labeled here by the letter P. If we were to take this a step further and zoom into the proton, we would see that the proton is actually made up of even smaller particles called quarks, labeled here by the letter Q. In addition to these quarks, the proton also contains a huge number of particles called gluons. And the gluons, labeled here by the letter G, literally act like the glue which holds the quarks together inside of the proton. If we were to take this a step further and zoom into the quarks, we would see that the quarks are made up of, well, we have no idea. In a sense, this is one of the questions that we hope to answer at the Large Hadron Collider. So particles are sort of like the fundamental Lego blocks of our universe, but they actually play an even deeper role in our everyday experience. Particles are the fundamental messengers of information in our universe. You see, the human eye is actually a very sophisticated particle detector. In order for us to see an object like a tree, we need a source of light, like the sun, and light itself can actually be viewed as a stream of particles called photons, labeled here by the Greek letter gamma. Millions of these photons coming from the sun scatter off the tree and into our eyeballs. The angle at which they enter our eyeballs depends on the location at which they scatter off of the tree, but our eyes have evolved to decode this pattern into a visual signal that our brains can recognize as a tree. At the particle level, we would see that these photons are actually scattering off of the electrons in the atoms of the tree. And so particle-particle scattering is the fundamental mechanism that allows humans to see things. In order to discover new particles of nature, scientists built the Large Hadron Collider, or the LHC for short. This is a picture of the LHC from an aerial view. It consists of a 27-kilometer ring that straddles the borders of Switzerland and France. Using high-powered magnets, physicists send bunches of protons in opposite directions around the ring until they reach very close to the speed of light. And then it sets them to collide at 4 specific points around the ring, where 4 different detectors are set up to collect debris from the collision. These detectors are named ATLAS, ALICE, CMS, and LHCb. In the QuarkNet Masterclass, we will be analyzing the data from ATLAS. And ATLAS is a giant cylindrical all-purpose particle detector. Bunches of protons enter the cylinder from opposite ends and collide at the center, where detectors are set up to analyze the debris from the collision. According to the laws of physics, everything that happens in the universe is the result of particle interactions. The standard model of particle physics gives a complete list of the known fundamental particles of nature and fits them into a neat, beautiful pattern as indicated by the chart here. The particles on the outer edge of the ring form the basic building blocks for all the known matter in the universe, and they can be divided into 2 categories. In red, we have the quarks, and the most familiar examples of quarks are the up and the down quarks, which come together to form the protons that sit at the center of all atoms. In green, we have the leptons, and the most famous example of a lepton is the electron, which binds with the protons in the atoms. In blue, we have the force particles. We've already been introduced to the gluon, which is the particle that's responsible for keeping the up and the down quarks tied together inside the proton. And we've also been introduced to the photon, which is the particle that's responsible for communicating the sensation of human vision. At the center, we have the mysterious Higgs boson, which ties all of the known fundamental particles together. I should also mention that for each matter particle, there exists an antiparticle, which is indicated by a bar over the particle name. Particles and antiparticles are identical in every single way, except they have opposite electric charge. In addition to providing us a list of the known particle species, it also gives us a list of rules for how the different particles can change into one another, and how often this should happen. This will be crucial for allowing us to identify some of the more exotic particle states, such as the Z boson and the famous Higgs particle. Here is a list of some of the rules that will be important for us. According to the Standard Model, if we were to create a Z boson, we would find that it would decay about 3.3% of the time to an electron and its antiparticle. The Standard Model also says that the Z boson treats all leptons identically. This means that the Z boson will also decay to a muon and its antiparticle about 3.3% of the time as well. Another set of rules that will be important for us is how the Higgs boson decays. According to the Standard Model, a Higgs particle will decay to two Z bosons about 2.7% of the time, and about 0.2% of the time, it will decay to a pair of photons. These rules also give us a picture for how particles like the Z boson can be created at the Large Hadron Collider. For example, when we collide two protons, a gluon from one of the protons can split into a quark and its antiquark partner. The antiquark can combine with a quark from the other proton to form a Z boson. Similarly, a Higgs boson can be created in the collision of two protons when the gluon from one proton fuses with the gluon from another proton to create a Higgs boson. One of the biggest challenges to discovering particles like the Z boson and the Higgs boson is due to the fact that they're actually relatively difficult to produce at colliders like the LHC. In order to understand why, we need to think about Einstein's famous equation, E equals mc squared. Here E stands for energy, m stands for mass, and c stands for the speed of light. This equation tells us that mass is really a form of energy, and that we can think of the speed of light as the conversion factor between these two equivalent substances. This means that energy can be converted into mass, and likewise, mass can be converted into energy. For this reason, physicists often find it convenient to talk about a particle's mass in units of GeV over c squared. To keep it simple, I can tell you that 1 GeV per c squared is equal to about 1.7 times 10 to the minus 27 kilograms. How heavy is a proton in these units? In units of GeV over c squared, a proton has a mass of about 1. So its mass is very close to 1.78 times 10 to the minus 27 kilograms. In comparison, a particle like the Z boson is about 91 times heavier than a proton. And a particle like the Higgs is about 126 times heavier. This means that in order to have any chance of producing a Z boson or a Higgs boson, we need to collide the protons with extraordinarily high energies. Because Higgs bosons are produced so rarely at the LHC, we need a reliable way of separating out the small number of collisions that produce Higgs bosons, which we can refer to as signal, from the huge number of events that do not produce Higgs bosons, which we can refer to as the background. For example, we know that two protons can come together and fuse to form a Higgs boson, and that Higgs boson can subsequently decay into two particles of light, which we can label gamma 1 and gamma 2. However, for every single time that this happens, there will be a huge number of occurrences where the two protons can fuse together and form two particles of light without producing a Higgs boson. Because the particle detectors are only capable of detecting the final debris from the collision, it might seem impossible to disentangle these two processes. However, we can use our knowledge of physics to separate them. In particular, we can use the fact that energy is conserved throughout the processes. This means that if I add up the two energies of the two photons in the signal process, according to Einstein's equation, I must get something that is equal to the mass of the Higgs times the speed of light squared. Whereas if I add up the energies of the two photons in a non-Higgs event, I'll get something that's relatively random. So the strategy is to go through all of the events and pick all of the events that have two photons in the final state. Then plot the sum of the total energy of those two photons, which we refer to here as E gamma gamma. In the events that produce the Higgs boson, the events should pile up at around the mass of the Higgs times c squared. And the events without a Higgs boson will be relatively randomly distributed. We can therefore identify the events with the Higgs boson as a small bump of the signal above the background distribution.